far beyond the reach of our solar system, past the twinkling stars that color our night sky, and deeper still into the cosmic sea of light and dust, lies a gaping void so colossal, so powerful, and so mysterious that it has captured the gaze and wonder of astronomers for decades. It doesn't just sit at the center of a galaxy, it commands it. This is M87, the supermassive black hole lurking in the heart of the elliptical galaxy Messier 87, and it's nothing short of a cosmic titan. If you gazed up into the constellation Virgo with the sharpest eyes in the universe, or better yet, with the world's most advanced radio telescopes, your vision might just pierce 55 million light years of space to glimpse the home of M87. What you wouldn't see with the naked eye, however, is that at the core of this ancient galaxy resides something staggering, a black hole with a mass more than 6.5 billion times that of our Sun. Not million, billion. To grasp that size is to test the limits of human scale. If our Sun were a grain of sand, M87 place would be a mountain. This black hole is so immense, it could fit our entire solar system, and then some, within its event horizon, the point of no return. Any star, planet, asteroid, or even light itself that crosses this invisible boundary is simply gone, devoured in an instant, never to escape again. In April of 2019, the world stood still as one singular, fiery orange image made history, a blurry ring of light around a dark core, a shadow stitched by gravity into the very structure of the universe. The first photo of a black hole, not just any black hole either, this black hole, M87 Huis, that grainy golden halo was a silhouette against cosmic scales, proof of Albert Einstein's theories, and a doorway into the strangest depths of reality yet discovered. And while the photo was remarkable, it posed even bigger questions. How can something so far away, so invisible, and so incomprehensibly massive be seen? How does it even exist? And just how powerful is something like this? To understand M87 cog, we first need to understand its kingdom, the galaxy Messier 87, often described as a cosmic leviathan in its own right. Unlike our spiral-shaped Milky Way, M87 is an elliptical galaxy, a vast, balloon-like glow of ancient stars, gas, and dark matter. It's one of the largest galaxies in the nearby universe, and at its core sits the master, M87. For centuries, M87 was just another faint blur in the sky. Discovered in 1781 by Charles Messier, it was first known merely as Messier Object 87, a point of interest catalogued for telescope users. No one could have guessed there was a monster lurking at its center, not until the dawn of the 20th century, when astronomers began noticing something peculiar, a thin, piercing jet shooting out from the heart of this galaxy like an arrow across space. This wasn't a meteor. It wasn't a star trail. It was something else entirely. This jet spans over 5,000 light years, shooting straight into intergalactic space. That's longer than the distance from Earth to the nearest star outside our solar system by orders of magnitude. And what powered this jet? What could possibly be blasting energy and matter across that enormous stretch of space? All signs pointed inward to something dense, something spinning, and something incredibly hungry. Only a supermassive black hole could account for it. And thus began the pursuit of one of the universe's most enigmatic entities. For decades, M87 and its central engine became the subject of observation across radio waves, X rays, and visible light. Each new image deepened the mystery. Something in the center of M87 wasn't just collecting matter, it was violently consuming it and then ejecting it. It warped space around it, twisted magnetic fields, and unleashed gravitational effects so intense they could be measured millions of light years away. But still, we had never seen it until the team behind the Event Horizon Telescope, EHT, formed a plan. What if, instead of building a telescope as big as Earth, a physical impossibility, we used a network of telescopes across the globe to simulate one? Over time and immense collaboration, that's exactly what happened. And M87 Tix was chosen as one of the primary targets. Why? Because it was so big, so relatively close, and so immensely active. It was the perfect combination of cosmic luck and technological readiness. It was, in many ways, the low hanging fruit of black holes. If you can imagine calling something the size of billions of suns low hanging, when the image finally arrived in 2019, there was no mistaking what we were seeing: a black hole's shadow, framed by a glowing swirl of material collapsing endlessly inward. Light bent around it like water down a drain, the universe exhaling gas and dust into a perfect circle of obliteration. But here's the most haunting part. Everything you're about to learn, everything we know, is just scratching the surface. Because M87-6 isn't just a record breaking black hole, it is a gateway into a deeper understanding of what gravity, space, time, and even reality truly are. It challenges everything we think we know about physics. It whispers questions we don't yet know how to ask, and it stakes its dark claim over stars, matter, even information itself. You're not just going to learn about a black hole, you're going to feel the scale of it. Picture a region of space so powerful it could shape the motion of an entire galaxy, hundreds of billions of stars, all orbiting an invisible center like dancers swept into a whirlpool. That is M87, a silent puppeteer of cosmic proportions. And yet, like all things in the night sky, it is peaceful to observe. Its glow, its pull, is distant, calming, eternal. As we stand here on Earth, looking up in awe, the light that first escaped its nearby stars has been traveling for tens of millions of years to reach us through dark matter, starlit dust, and time itself, just to offer us a glimpse of its master. Welcome to M87, the monster at the edge of understanding. Now, let's unravel its secrets. Black holes are among the most intriguing and misunderstood objects in the universe. Yet, at their heart, they begin as something strikingly ordinary: a star. Not just any star, though. To become a black hole, a star must be massive, many times the size of our sun. And when that star reaches the end of its life, an extraordinary transformation begins, one that rewrites the rules of the physics. Imagine a colossal star burning for millions of years, its core fusing atoms to create heavier and heavier elements. But fusion isn't just an energy source, it's a delicate balancing act. Gravity is constantly trying to pull the star inward, crush it under its own weight, while nuclear fusion pushes outward, holding collapse at bay. For most of the star's life, this internal pressure wins, but eventually it doesn't. When a massive star exhausts all its nuclear fuel, fusion stops. Nothing remains to hold back the relentless pull of gravity. In a fraction of a second, its core collapses, crushing atoms, squeezing protons and electrons together, and imploding without resistance. What remains can become a neutron star, or, if the star was heavy enough, a black hole. But what is a black hole really? Is it a place? Is it an object? Is it an event? In truth, it's none of those things, and yet all of them. A black hole isn't an object the way we think of a planet or a star. At its center lies what physicists call a singularity, a point with infinite density where the known laws of physics, time, and space break down. We don't fully understand what exists at the singularity. It may hold the keys to other dimensions, or it could be the ultimate dead end of existence. Surrounding the singularity is a boundary known as the event horizon. It's invisible, not made of matter, but it defines the point beyond which nothing can escape, not even light. Once you cross it, your fate is sealed. Space and time distort so drastically inside this boundary that escape is, by all accounts, impossible. To better imagine it, think of space-time as a stretched out rubber sheet. If you place a bowling ball on it, the sheet dips deeply. That's how gravity works, warping the structure of space itself. A planet makes a small dip, a star, a deeper one, but a black hole? It doesn't make a dip. It tears right through it. It creates a well so steep, so infinitely deep, that the bottom simply isn't there. Not as we understand it. That's what makes black holes so strange. They don't suck like cosmic vacuums, despite the popular belief. They only pull on objects that come too close. If our sun were replaced by a black hole of equal mass, nothing drastic would happen to Earth's orbit. We'd keep revolving around it just as before, though of course, we'd lose all sunlight and life would cease. Still, the idea of total escape being impossible, it shakes something fundamental in us. What happens to time near a black hole? According to Einstein's theory of general relativity, time runs slower the closer you are to a gravitational source. Near a black hole, it slows to a crawl. At the event horizon, for an outside observer, time comes to a complete stop. Say you were watching a spaceship approach a black hole. As it neared the event horizon, its movements would slow, its lights would fade, and eventually it would appear to freeze in space, forever hovering at the edge. But from the point of view of someone on the ship, they'd be falling at full speed, plunging seamlessly past the horizon toward whatever awaits at the end. It's not just time that breaks near a black hole, it's space itself. Directions fold in strange ways. In falling toward the center, you're not just getting closer in space, you're also moving forward in time. In many thought experiments, once someone crosses the event horizon, they're not just falling toward a place, they're falling toward a moment, a future they cannot avoid. And what of the matter that falls in? It doesn't just vanish. According to classical physics, the information about it disappears, which creates a major conflict in modern science. The information paradox, as it's called, pits quantum theory, which says information is always preserved, with general relativity, which suggests it can be lost forever in a black hole. Solving this paradox has fueled decades of debates and led to groundbreaking work from physicists like Stephen Hawking. More recently, some scientists believe that black holes might not destroy information, but scramble it, locking it behind the event horizon in ways we don't yet understand. or even slowly release it back into the universe through a process known as Hawking radiation. This is where M87 begins to separate itself from the rest. You see, black holes come in different sizes. There are stellar mass black holes formed from individual stars, a few times the mass of our sun. Then there are supermassive black holes, millions to billions of times as massive, lurking at the centers of galaxies. Where stellar black holes are small and quick to form, supermassive ones, like M87c, are ancient, colossal, and their origins remain one of astronomy's greatest mysteries. How did M87c get so big? Did it grow by consuming stars and gas clouds over billions of years? Did it merge with other black holes in galactic collisions? Or was it born large in the early universe, during the first moments after the Big Bang, when conditions were still violent and exotic? There's no clear answer, but we do know this. Black holes, despite their terrifying reputation, aren't just destroyers. They play a vital role in shaping galaxies. The fierce winds and jets they produce can regulate star formation, blow away gas, and halt or trigger the growth of entire stellar systems. In a strange way, black holes might be part of the balance mechanism that keeps galaxies from overgrowing or collapsing inward. And this brings us full circle back to M87, because understanding how black holes operate is nowhere more urgent, more meaningful, or more fascinating than when studying a black hole like this one, a gravitational giant at the core of an entire galaxy, a lighthouse of energy, a deeply ancient and powerful force, silently sculpting the dynamics of the universe even now. In the vastness of M87, stars orbit at tremendous speeds, drawn inward by something they cannot see. Matter swirls into shining disks that vanish into the darkness. Plasma jets beam across space, and in the center of it all, a black hole larger than the mind can grasp, waiting, silent, immeasurable, and strangely beautiful. So when we ask, what is a black hole? We're not just asking about physics. We're asking about edges, edges of knowledge, edges of perception. And in the heart of M87 Nu, we find one of the sharpest edges of all. On a clear April morning in 2019, the world awoke to a sight previously confined to science fiction, a glowing ring of light circling the darkest shadow the universe has to offer. It was blurry by photographic standards, far from the crisp perfection of Hubble's glowing nebulae. But this image didn't need high definition to shake the foundations of science, because for the first time in history, humanity had captured a direct photo of a black hole, and not just any black hole, M87. Against impossible odds, we had managed to photograph something that doesn't emit light, that can't be seen in any conventional way, and that lurks 55 million light years across the cosmos. It was the visual confirmation of decades of theory, and it was achieved using one of the most ambitious, collaborative scientific undertakings the world has ever seen, the Event Horizon Telescope. To truly appreciate the magnitude of this achievement, we have to understand one critical fact. Photographing a black hole is like trying to take a picture of a grain of sand on the moon using a camera from Earth. The object is minute, in apparent size, incredibly far away, and shrouded by blinding light from its surroundings. And yet we did it. So how? The answer begins not with a single telescope, but with a network of them, strategically scattered across the globe. The Event Horizon Telescope, or EHT, isn't one telescope. It's a planet-sized array of observatories working together in perfect synchronization to function as one massive Earth-scale telescope. It's a technique known as Very Long Baseline Interferometry, or VLBI. The principle works like this. Two or more radio telescopes, separated by thousands of kilometers, observe the same object simultaneously. The signals they receive are time-stamped with atomic clocks accurate to a billionth of a second. By combining those signals, later using powerful supercomputers, astronomers can simulate the resolution of a telescope as wide as the distance between the furthest observatories. In this case, the array included locations from the South Pole to Europe, from Hawaii to Chile. Each telescope played a part, like instruments in an orchestra, gathering faint radio signals, specifically those generated by the intense heat of matter spiraling into M87's massive form. At the core of this method is the need to see through the dense fog surrounding the black hole. You can't photograph the singularity itself. Remember, nothing escapes from within the event horizon. Not light, not radiation, nothing. But you can see what surrounds it. And this is the key. As gas and dust fall inward, nearing the event horizon, they accelerate to incredible speeds, heating up to millions of degrees in a superheated plasma accretion disk. That disk glows in radio and X-ray wavelengths, creating a luminous ring around what appears to be a dark, circular shadow, the silhouette of the black hole. And that's what the EHT captured, the image we now all recognize. A fiery halo with a dark center is not the black hole itself, but its shadow caused by the gravitational bending and capture of light by the event horizon. The light that escapes does so just barely, and does so in a way that lets us see the outer boundary of the black hole's domain. The bombardment of data collected during EHT's campaign in April 2017 was enormous. In fact, the sheer volume, over 5 petabytes, or about 5,000 full human years worth of HD video, was too large to be transferred over the internet. Instead, it had to be shipped physically via specialized hard drives, flown to central processing locations. From there began a painstaking, collaborative effort between hundreds of scientists, engineers, and mathematicians from across the globe to reconstruct the image from noisy, scattered data. 4 independent teams worked separately to prevent bias, each using different algorithms. When all 4 produced highly similar images, the confidence was staggering. The ring shape, the dark center, the orientation, all matched theoretical predictions from relativity nearly perfectly. But this wasn't just a random, artistic rendering brought to life. Every pixel in the image corresponds to real light, real data, real physics. It was iconic because it was observed, no longer a digital simulation or abstract calculation, but physical evidence of a force so powerful it traps even light. And the target, M87 Briggs, was not chosen lightly. Initially, there were 2 primary candidates for the first black hole image, M87 and Sagittarius A, the supermassive black hole at the center of our own Milky Way. Both were ideal in terms of apparent size in the sky. Despite their differences, Sagittarius A is much closer, at about 27,000 light years, but significantly smaller in mass. M87 was further away, but far larger, with a radius reaching billions of kilometers. Ironically, M87 proved easier to image despite its distance. Why? Because Sagittarius A Star is relatively active and variable. Its accretion disk changes rapidly, even minute to minute, while M87T's structure is surprisingly stable over longer timescales. That stability allowed the EHT teams to work with a more consistent source of light, leading to a clearer final result. The final image wasn't just inspiring, it was profoundly validating. It matched predictions first made by Einstein's theory of general relativity over a century ago, down to the size and shape of the black hole's shadow. It served as one of the most critical confirmations of relativity in extreme cosmic conditions. A theory born from chalkboards and ink in 1915 had suddenly been tested and passed by the furnace of a supermassive black hole 55 million light years away. But the image was not an endpoint. Rather, it was a cosmic door opened wider than ever before. It was proof that with the right technology, the right teamwork, and the right questions, we can explore the nature of gravity, matter, space, and time in their most extreme environments. The EHT has already gone on to image Sagittarius A Sor, publish improved models of M87 TOE, and continues to gather data on black holes around the universe. The possibilities are expanding. Future upgrades may allow real-time imaging, deeper resolutions, even short videos showing the movement of plasma around black holes. Perhaps one day we'll witness a star consumed frame by frame, a silent collapse visible from across the vastness of light years. We are now pioneers, peering into the darkest hearts of galaxies, not through poetic imagination, but through measurable light, harnessed and stitched together by human ingenuity. The photograph of M87 became more than just an image. It became a symbol of collaboration across nations, of physics brought to life, and of the enduring human desire to understand not just the stars, but the great shadows between them and what shadows they are. In the case of M87 Tux, a shadow cast by something so powerful, so utterly immense, it shaped an entire galaxy, ejected jets of matter tearing across intergalactic space, and still, somehow, sits in patient silence, tugging at the fabric of the universe from its invisible throne. This image gave us a face, not of a monster, but of one of the universe's oldest, quietest architects, and we are only beginning to understand what it's trying to show us. Power. In the cosmic theater, it is measured not just by how much something glows, but by how much it moves, bends, controls, and overwhelms everything around it. And when it comes to raw, uncontested force, few objects in the universe can rival M87, the supermassive black hole at the heart of the giant elliptical galaxy, Messier 87. This is no ordinary gravitational well. This is a beast of such unimaginable scale that it defies intuition. A 6.5 billion solar mass void, a central engine that steers an entire galaxy of hundreds of billions of stars. It's been quietly reigning for billions of years, shaping the behavior of everything within its dominion, and even flinging material into the vast intergalactic void. To start grasping the magnitude of M87, forget anything you know about planets, stars, or even other black holes. This is a supermassive black hole, and it's bigger than our entire solar system. Its event horizon The boundary, beyond which not even light can return, spans approximately 38 billion kilometers. That's about 250 times the distance between Earth and the Sun, or nearly 5 times the distance from the Sun to Pluto. Now pause for a moment and imagine that a singularity so dense, with gravity so overwhelming that even photons, the fastest travelers in the universe, cannot escape its grip. But M87 doesn't just consume, it also creates one of the most powerful phenomena in astrophysics: relativistic jets. From the poles of M87T, two enormous jets of charged particles blast out at near light speed, extending over 5,000 light years into space. That distance is mind bending. It's longer than the span of the Milky Way's entire galactic disk. And these are not quiet gusts, they are weaponized rivers of plasma, composed of electrons and other subatomic particles traveling at 99% the speed of light, tearing through the vacuum of space. These jets are the signature of a rare balance, where sheer gravity meets sheer motion, as matter spirals into the black hole's whirling accretion disk. Some of it gets caught in powerful magnetic fields and is ejected at unimaginable velocities. And while we can't see M87 directly, we can see the glow from these jets. They're so bright that they can be observed with basic amateur telescopes from Earth, the visible aftershock of a beast feeding in silence. This staggering energy output, known as the active galactic nucleus, can sometimes outshine the entire light from the rest of the galaxy. Yes, that's how bright this process can be, brighter than all the stars in M87 combined. And yet, despite unleashing such fury, M87 is astoundingly stable. It's not a churning, chaotic force, as one might imagine. It's a slowly spinning, reliably feeding giant. Unlike smaller black holes, which can flicker like unreliable flames, M87 churns like a deep, slow-burning engine, its immense size making it slow to evolve, but also incredibly predictable. Now comes the question that inevitably follows. How did something so powerful come to be? There are several theories, though none offer complete certainty. One possibility is that M87 was born massive in the ultra-dense chaos of the early universe, formed from primordial gas clouds that collapsed directly into black holes without first forming stars. Another possibility is that it grew over time, step by step, devouring stars, gas clouds, and other black holes as galaxies merged and collided in the ancient cosmic dance. However it formed, its presence today is a defining force, literally shaping the structure of its host galaxy. One might assume black holes just sit idly, waiting to feast, but in reality, they play active roles in galactic ecosystems. M87 controls the fate of star formation in its region by disturbing and heating up the interstellar gas around it. If the gas cannot cool and collapse, new stars cannot form. In this way, M87 acts like a cosmic regulator, deciding when and where a galaxy may continue to grow. It's this interplay between destruction and creation that makes M87 more than just a gravitational sinkhole. It's an anchor, a governor, and a guardian. Its immense power, both a threat and a balancing force. Let's break down a few of the numbers to put this power into perspective. Mass: 6.5 billion solar masses. That's about 2 quintillion times the mass of Earth. Written out That's a 2 followed by 18 zeros. Gravitational pull at its event horizon, so strong that to escape, you'd need to travel faster than light, something nothing in our universe can do. Jet energy output, more than 1 trillion times the energy consumption of all human civilization combined. Time span, M87, has likely existed for more than 10 billion years, meaning it's been active for most of the universe's history. When you scale things to this level, normal physics begins to feel like a child's game. Even our largest machines, our grandest theories, strain under the weight of what M87 represents. Time, space, matter, all kneel in its presence, and yet it's still just one black hole among perhaps trillions in the universe. But make no mistake, it is special, not just because we photographed it, not just because of its immense size, but because it's the first one we truly saw, the first deep window into the abyss, and what we learned from it continues to shape our understanding of the cosmos's most extreme environments. Even now, scientists continue to model and simulate the behavior of M87 Takir, its spin, its feeding patterns, its jet formations, all to better understand what role such giants play in a universe still unfolding. Through simulations fed by real data, we're beginning to animate M87 codes, to see the swirl of its disk, to calculate the way light bends and dances around its ferocious gravity. There's something poetic here. In the middle of an ancient galaxy, shrouded in darkness and silence, exists one of the most powerful forces in the universe. And we, tiny inhabitants of a distant blue dot, have managed to glimpse its wrath, its beauty, and its truth. M87 is not violent for the sake of violence. It's not alive. It's not watching. It simply is a natural consequence of mass, density, and time folding together into form. But through understanding its power, we better understand our universe. We start to see the hidden engines behind the galaxies. We see the invisible hands sculpting the cosmos. And we see, perhaps most humbling of all, how small we truly are and how magnificent the universe must be to contain something like this. And yet, its story doesn't end here, because the most terrifying question of all still lies ahead. What would happen if we got too close? And in the next chapter, we'll follow that journey, step by step, into the mouth of the abyss. You're floating alone in the vastness of space. Stars glimmer like scattered diamonds across a pitch black sea, utterly silent and serene. But ahead, looming in the void, is something darker than darkness itself. At first, it's nearly invisible, a shadow barely distinguishable against the background. But as you drift closer, its presence begins to take shape. You don't see it directly. You see the absence it creates, light bending and distorting around a central, perfect void. You are approaching M87, the supermassive black hole, and you're falling in. What would that feel like? What would happen? Let's imagine that journey, not just in scientific terms, but as a human experience. Strap in, because from this point on, you're not just learning about a black hole, you're falling into one. As you approach, distant stars begin to warp. The fabric of space doesn't behave the way you're used to. Light doesn't travel in straight lines anymore. Ahead, you see a glowing halo, the accretion disk. It spins with fury, gas and dust swirling around the black hole at near the speed of light, superheated to millions of degrees and glowing with a terrible beauty. Radiation crackles invisibly around you. The ship's shielding holds. You're safe. For now. The first thing you notice is that time begins to act differently. To you, everything feels normal. Seconds ticking by as always. But for an observer watching from afar, time around you begins to slow. As Einstein predicted with his theory of general relativity, gravity isn't just pulling you, it's bending time itself. To the outside universe, you appear to move in slow motion. As you continue toward the event horizon, this effect becomes more extreme. From Earth, it would look like your ship freezes, hovering just above the edge forever, growing redder and dimmer as light struggles to escape it. But you don't feel this. From your perspective, you pass right through, smoothly, silently, without fanfare. This is the event horizon, the invisible boundary surrounding M87K, where escape velocity, the speed you'd need to get away, exceeds the speed of light. Nothing beyond this can return. Not data, not light, not even hope. And now, you're inside. This is uncharted territory, where physics, as we understand them, begin to break down. Inside the event horizon, the dimensions of reality begin to shift in eerie ways. Space becomes time. Time becomes space. Imagine falling toward a point in space, but that point is also in your future, and you cannot avoid it. Here, all paths, no matter how you try to maneuver, lead to the singularity, the central point of infinite density at the black hole's heart. As you fall, you notice that the laws of motion no longer behave normally. The forces pulling you are not just strong, they're absolute. Every particle of your body is now being tugged inward, and the difference between the gravity at your feet and your head becomes extreme. This is what scientists call spaghettification. You're being stretched, not metaphorically, literally. The tidal gravitational forces begin pulling you apart with such intensity that atoms themselves would start to stretch. If you entered feet first, they would begin falling faster than your head, pulling you into an elongated filament of matter. In a smaller black hole, this would happen before you even reached the event horizon. Strangely, in a supermassive black hole like M87X, those gravitational gradients at the horizon are weaker. So in this case, you might not feel anything unusual at the crossing point. But the deeper you go, it's inevitable. Inside the event horizon, the rules are gone. All matter is rushing toward a central point from which no information can escape. Scientists believe the singularity is a place of infinite density and zero volume, a breakdown in space-time itself. But no one really knows what happens there. No telescope can see it, and no signal can be sent out. There are theories, of course. In some models, a singularity is the ultimate endpoint. Nothing escapes. Everything that has fallen in is eternally compressed into the smallest possible point, erased from meaningful existence. In others, quantum effects come into play. Perhaps the information is stored somehow in the event horizon's surface as quantum bits, a theory that arises from the idea that black holes have entropy and, strangely, even temperature. This led to one of the most curious realizations in modern physics. Black holes may eventually evaporate through a process known as Hawking radiation, but M87 Kais is so massive, its theoretical evaporation would take much longer than the age of the universe. So, from any practical perspective, once you're in forever. Does that mean death? Maybe. But here's the strange twist. We don't actually know what happens to you. Some physicists propose that you experience nothing out of the ordinary, even as you fall into the singularity. Others suggest you might be compressed out of existence, and a few wonder, what if the singularity is actually a bridge? This leads us into the concept of wormholes, tunnels through space-time that might connect distant parts of the universe, or even different universes altogether. Could the singularity be an opening to another realm? Could what goes in emerge somewhere else? Science doesn't have the answer. Not yet. What we do know is this: the closer you get to the singularity, the more time compresses. In some scenarios, you might experience the far future in mere seconds. The entire universe could end in the outside timeline while you continue falling inward. Time, from your perspective, might never end. In that sense, to cross into a black hole is to step out of the universe as we know it, not just in space, but in time. You no longer exist in a meaningful way to the rest of the cosmos. Your future is detached from theirs. It's not death exactly, but it's certainly not life in any ordinary form. It's something else. So why would we even imagine this descent? Because it stretches the mind. It challenges everything we believe about reality, about beginnings and endings, about physics, about perception. M87, in all its terrifying brilliance, remains strangely peaceful from afar. From Earth, or a telescope's lens, it spins quietly, steadily, as it likely has for billions of years. Its silence makes it no less powerful. If anything, it enhances the mystery. We look at images of it and feel awe, not fear. But the truth is, at the heart of this quiet shadow is a force so immense, so precise, so inescapable, that even approaching it begins to disassemble not just your atoms, but your sense of what is real. And here's the haunting part. Right now, as you read these words, stars are falling into it, gas clouds, dust, possibly even planets and debris, swallowed whole and gone. But to M87, it is nothing, no sound, no flicker of acknowledgement, just the same slow turning of space and time, just the same dark sphere framed by light, unmoved, unmatched. That is the power of a black hole, not chaos, control. And in the next chapter, we'll look outward again, back to the light around M87 Hain, and unravel how it bends everything in its presence, not just in space, but in time itself. The stars don't appear where they should. As you drift near M87 Ephemerix, the light from distant galaxies bends, warps, and distorts, forming shimmering rings and twisted arcs that wrap around nothingness. It's as if you're seeing the universe reflected in a funhouse mirror, only the mirror isn't made of glass. It's made of gravity, intense, curved gravity, space itself. This is the strange magic of M80 Svento, a black hole not just powerful in mass, but powerful in its power to reshape reality. It doesn't scream its force the way an exploding star might. Instead, it bends the rules, quietly, smoothly, inevitably. When Einstein first proposed his theory of general relativity in 1915, he revolutionized our understanding of gravity. He revealed it not as a force between masses, like Newton believed, but as a warping of the fabric of spacetime itself. Massive objects like stars, planets, and black holes don't just sit in space, they shape it, bend it, and the deeper the mass concentration, the deeper the curve. Black holes represent the steepest curves imaginable, and M87, with more than 6.5 billion times the mass of the Sun, is the ultimate sculptor, not only folding space, but twisting time itself around its immense core. Picture space like a stretched rubber sheet. A bowling ball placed on the sheet creates a dip. Now replace the bowling ball with a truck. That's M87 tour. The dip becomes so extreme, it becomes a well so deep that nothing, not even light, can climb back out once fallen in. But the effects of that dip reach far beyond the hole's edge. As light from background stars passes near the black hole, gravity bends its path like a beam of light passing through a lens. This phenomenon, called gravitational lensing, doesn't just alter our perception of starlight, it shows us how gravity literally alters the path of light itself. And because time and space are part of the same fabric, what Einstein called space-time, when space is warped, time is too. Near M87 new, time slows down, not metaphorically, measurably. Clocks tick slower compared to those further away. This isn't science fiction, it's physics. Satellites orbiting Earth need to account for this very effect, or things like GPS wouldn't work properly. Near a black hole, it becomes dramatic. At the event horizon of M87 tons, time for an external observer effectively stops. A journey to the edge of this gravitational abyss becomes a journey not just through space, but into a future that exists outside the traveler's experience. All of this reveals something deeply profound. M87 isn't just a hole in space, it's a tear in the flow of time itself. What you see, what you feel, even what you are, begins to shift under these conditions. The usual frame of reference becomes meaningless. Directions distort. Paths of motion curve permanently. If you tried to fly around the black hole, you'd find space itself resisting, pulling you subtly inward no matter your heading, like trying to run uphill from every side of a valley. But things get weirder the closer you get. In deep gravitational wells, like M87 TOS, something called frame dragging can occur. This happens when the black hole itself is spinning, which most are believed to do. Their rotation literally twists space-time around them. It would be like stirring a spoon in honey and seeing everything nearby start to swirl. M87's massive spin causes even light and time to be dragged along with it. If you tried to hover near its rotating edge, you'd find yourself unwillingly pulled into orbit by twisted space-time itself. This spinning of space has scientific implications so bizarre it almost sounds spiritual. Inside certain theoretical boundaries, time and cause can become so bent that in some equations, closed loops in time emerge. These are the mathematical beginnings of something often dubbed a time machine, a path where, in theory, you could return to a previous point in time. But could such loops exist near M87 twice? Could black holes really allow time travel? The prevailing view: no, not in the way we fantasize. The physics becomes unstable. The energies involved infinite. These are things nature, so far as we understand, tends to avoid. But the mere possibility that curved space-time could theoretically allow such behavior, that alone is breathtaking. But even if time loops are myths, lensing is not. Some of the light that's bent around a black hole is bent again and again, multiple times. This can create photon rings, layers of light orbiting the black hole a fraction of a second before plunging in. The brighter halo seen in M87T's photo is partially composed of these photons making their final orbits, their paths spiraling so tightly that light is essentially circling the black hole endlessly. The deeper consequence? A black hole doesn't just capture light, it becomes part of the scenery, reshaping the entire visual appearance of the universe around it. Even the way the accretion disk looks is changed. To us, we see the top, the bottom, and even part of the backside of the disk at once. Light from behind the black hole curves around and reaches us. No other object can do this. The view near a black hole is one of the most alien perspectives possible in known physics. And yet, we can predict it. Einstein's theory has proven correct again and again, from a black hole mergers to gravitational lensing around galaxies to the behavior of time near intense gravity. And when we look at M87 Hui, we see not just light and darkness, but a test of physics at its extreme, the bending of light, the warping of time, the convergence of mass into invisible space. These are not distant ideas anymore. They are real, visual, and now measurable thanks to the image of M87 tags. We're watching the very blueprint of the universe deform under weight we can now almost comprehend, and it leads to the ultimate question. If time and space can bend around M87 chord, what happens beyond the point of no return? Beyond the lensing, the stretching, the silence, what lies after the fall? In the next chapter, we descend even deeper, not into space or time, but into speculation, where science meets imagination, where the singularity sits, where theories collapse, and where perhaps the universe has something waiting on the other side. Beyond the luminous halo, past the photon rings and warped light, lies a darkness so complete it has no color, no edge, and no dimension we can describe. It's not simply the absence of light, it's the absence of knowing. This is the realm inside, the event horizon of M87 Tech, the shadowed world beyond our reach. No telescope can penetrate it, no signal can escape it, nothing we send in, no probe, no light beam, no whisper of radio waves, returns. So what exists beyond the event horizon? The honest answer is haunting. We don't know. Not really. Not completely. And perhaps we may never truly know. But this is where science becomes its most exciting. Not in certainty, but in the silence just past it. In this chapter, we step into that silence, into the unknown. Let's start with what we do expect. When something crosses the event horizon of M87 tanks, it falls inward with no hope of turning back. From an outside perspective, as we've seen, it seems to freeze in time, fading as its light redshifts into the infrared and disappears. But within, from the falling object's perspective, things continue. The unfortunate traveler doesn't feel a jolt or a boundary. It's not like passing through a wall. Entry into the event horizon feels just like drifting anywhere else, in space. At first, then comes the fall, an unstoppable, inescapable descent toward the heart of the black hole, the singularity. This is a one-way journey. In general relativity, all paths within the event horizon point inward. Direction itself is redefined. Every possible motion carries you closer to the core, as surely as time always carries us toward the future. To fall into a black hole is to follow a path where space moves like time, irreversible and relentless. The singularity is the ultimate unknown. According to Einstein's equations, it's a point of infinite density and zero volume, an extremity where the curvature of spacetime becomes infinite and the known laws of physics collapse. But infinities like these raise alarm bells for physicists. They're often signs that the theory in use, no matter how brilliant, has reached its breaking point. And here lies the truth. General relativity is incomplete. It predicts the formation of singularities, yes, but it cannot describe them. It offers no accounting for the quantum effects certain to arise when spacetime is compressed to scales smaller than atoms, smaller than particles, down to what we call the Planck length, the smallest meaningful unit of space in the universe. This is where classical physics gives way to the strange and jittery realm of quantum mechanics, and blending the two is one of the greatest unsolved goals of modern science, the quest for a quantum theory of gravity. Some physicists believe that such a theory would smooth out the singularity, cut off the infinities, tame the equations, and describe what truly lies beyond the event horizon. Until then, we're left with brilliant speculation and frameworks of possibility. Could the singularity be a gateway? One possibility, still theoretical and controversial, is that black holes, instead of simply ending all paths, could open new ones. In certain solutions of Einstein's field equations, especially those involving electric charge or rotation, black holes can be described as having more than one region. These mathematical models hint at bridges between distant points in space, or even between two universes. You might know them as wormholes. Could M87 be a mouth to such a passage? A wormhole, in theory, is a tunnel through spacetime, a shortcut connecting two distant regions. These concepts appear in solutions like the Einstein-Rosen bridge, but traversable wormholes would require something exotic to stabilize them: negative energy or exotic matter with properties not observed in nature. Still, physicists like Kip Thorne and others have explored the idea, and wormholes remain fertile ground for thought experiments and science fiction. But 879, as far as we can tell, behaves like a classical black hole. No evidence of a wormhole, no visible other side. And yet the math doesn't rule it out completely. Then there's the black hole cosmology hypothesis, a radical idea suggesting that every black hole might give birth to a new universe. In this view, the singularity doesn't destroy information or crush it into nothing. Instead, it becomes the genesis of a separate realm, a new Big Bang, sealed off from our own. From inside, that universe would look like its own cosmos, unaware of the black hole it emerged from. This idea is neat, elegant, intriguing, but highly speculative. So too is the concept that all information falling into a black hole gets stored on its event horizon, as if the surface encodes a holographic imprint. This concept, called the holographic principle, stems from string theory and the work of scientists like Leonard Susskind. It provides a possible way to resolve the black hole information paradox, a puzzle first identified by Stephen Hawking. The paradox is simple, but strange. If things fall into a black hole and are never seen again, is information truly lost? That defies quantum theory, where all processes are thought to be reversible, and information can't simply vanish from reality. In the 1970s, Hawking showed that black holes aren't entirely black. They emit what we now call Hawking radiation, a slow trickle of quantum particles caused by virtual particle antiparticle pairs near the event horizon over long enough timescales. This effect suggests that black holes will slowly evaporate, disappearing into nothing. But if the black hole vanishes and its contents were lost forever, information is destroyed, and that breaks the very foundation of quantum mechanics. So which is right, relativity or quantum theory? That's the battleground where the frontier of physics lies today. Emerging ideas such as firewalls, fuzzballs, and even modifications of Hawking's original theory offer competing views. One theory suggests that the edge of a black hole might actually be a chaotic, energetic furnace, a firewall that incinerates anything that crosses it. Another posits that quantum strings replace the notion of a singular point, spreading matter into a fuzzball that avoids a true interior at all. Others argue that the answer lies in entanglement, a connection between particles once in contact that persists no matter how far apart they are. Perhaps the interior of the black hole is somehow a continuation of the outside, entangled so deeply that the separation is merely an illusion. In all of this, one thing becomes clear: black holes are not simple graves. They're not voids where matter simply ends. They are active, complex players in the quantum landscape of the universe. And M87, as a supermassive black hole, might contain countless narratives folded into its gravitational depths. Collapsed stars, fragments of ancient galaxies, whispers of the early universe, millions, perhaps billions of years' worth of cosmic material has fallen into it. What has become of it? Reduced to math? Preserved in a hologram on its edge? Spawned into something we cannot yet detect? We don't know. And strangely, that not knowing may be the point, because while black holes might be the ultimate erasers of detail, they may also be the most concentrated archives in the cosmos, containing not just mass, but memory. Deep inside M87, past the swirling glow and the shadowed ring, might lie the story of 1,000 fallen suns, the collapsed cores of forgotten worlds, and perhaps the birthplace of something we cannot yet imagine. In the next chapter, we'll raise an even stranger possibility. What if black holes themselves, like M87 too, hold not just mass and energy, but meaning? What if they aren't just ends, but instruments of intelligence, computation, or even design? What if in staring at the darkest places in the universe, we're seeing something thinking back? From the outside, M87 appears quiet, patient, eternal. It spins in solitude among a galaxy of drifting stars, swallowing light, bending space, distorting time, without sound or signal. But in its silence lies a growing question, one that reaches beyond physics and touches the edge of philosophy. Could a black hole be more than just a gravitational object? Could it somehow process something? Could it think? It sounds like science fiction, and perhaps, in some ways, it is. But as we dive deeper into the nature of M87 Tir and of black holes themselves, we find ourselves standing at the intersection of cosmology and computation, consciousness and physics, a place where bold new theories begin to emerge. Because what if black holes are not just ends of matter, but beginnings of a kind of cosmic brain? The idea is bold but intriguing. Let's start with something that seems unrelated at first: computation. In our world, a computer is a system that takes in information, processes it, and gives a result. The brain, too, is a kind of computer: biological, chemical, and enormously complex. It processes vast amounts of information and turns sensation into awareness. Now consider this: the universe itself follows laws. Particles interact through rules. Conditions evolve in repeatable ways, and systems operate like programs. This has led some scientists to ask, if the universe acts like a computer, could it be one? This is the root of the digital physics hypothesis: the idea that the universe is inherently computable and that fundamental elements of matter and energy can be thought of as forms of information. And this circles us back to black holes. Stephen Hawking, in his groundbreaking work, helped show that black holes are not entirely black. They emit Hawking radiation, gradually evaporating over time. But more importantly, he paved the way for a realization that shook physics. Black holes have entropy. Entropy is a measure of disorder, or more usefully, information content. The surface area of a black hole's event horizon determines its entropy, and that surface area sets a limit. It tells us how much information the black hole has absorbed. That means every star, every planet, every atom that falls into M87, however shredded, compressed, or erased, still adds to its information storage. In a strange, deep way, it's like a cosmic hard drive, with writing happening not inside it, but literally on its surface, the event horizon. This idea led to an even deeper revelation: the holographic principle, proposed by physicists like Gerard de Hooft and Leonard Susskind and influenced by string theory. This principle suggests that all the information within a volume of space can be encoded on its boundary, not just black holes, but perhaps the universe itself. Think about that. It means the interior of M87 Tau, in all its unfathomable detail, might be mathematically equivalent to data etched on its 2D surface, just like a hologram stores a 3D image in 2D light patterns. So, what does this have to do with intelligence? Well, if black holes store information and evolve over time and interact with other systems and even emit radiation that may carry bits of encoded detail, are they not, in a distant and theoretical sense, processing information? Some scientists have taken this idea further. Could black holes act as natural computers? Cosmic machines operating at the edge of physics, compressing, encoding, and transforming data at scales beyond our imagination? Physicist Seth Lloyd once proposed a provocative idea: that the universe itself could be seen as a quantum computer, and black holes as the ultimate processing units within it. According to Lloyd's estimates, black holes, including giants like M87T, are capable of performing more computations per second than anything else known. By that reasoning, M87 SAX may be the most powerful processor in the known universe, not a conscious one in the human sense, not something with thoughts and feelings, but a system that takes inputs, obeys fundamental rules, transforms energy, and stores outcomes. In this strange framework, black holes are nature's answer to questions we haven't even asked. Yet, but not all theories stop at Computation. Some philosophers and theoretical physicists have even entertained the shadow of a bolder thought. Are black holes manifestations of some deeper cosmic structure, even intelligence? This doesn't mean they think consciously. There's no personality in the shadow of M87 ducks. But perhaps intelligence, real universe spanning intelligence, does not look like us. Perhaps it does not arise in brains, neurons, or circuits, but in processing systems far larger, older, and more alien than anything we can conceive. It's an unsettling idea. It would mean intelligence, rather than being something tied to biology, could exist in form and function only, not mind. It would suggest that what we call mind may just be the crude beginning of something far stranger, something the universe builds not in flesh, but in fire, gravity, and time. M87 may just be a piece of that structure. Now, let's temper wonder with caution. These ideas are highly speculative. The idea of a black hole as a computer, or even an unconscious thinker, is still far outside the mainstream. Most astrophysicists focus on the observable and measurable aspects of black holes: mass, spin, charge, radiation, and rightly so. But even in conservative models, we do see black holes as halos of complexity and mystery. They are informational bottlenecks. They are entropy machines. They are natural laboratories for quantum gravity, where the bone deep truths of space time are exposed like nerve endings. Even if they aren't brains, even if they aren't minds, they are places where reality is at its most raw, where physics itself seems to reconsider the rules. And that's enough to warrant awe, because if you're a civilization trying to understand the universe, if you're a species curious about yourself, there may be no greater mirror than a black hole. They reflect not our image, but our ignorance. They show us where we stop, where understanding ends, where answers dissolve into questions. 87, gorging silently in a distant corner of the Virgo cluster, doesn't whisper messages, but hidden in its jet streams, in its radius, in its gravitational signature, are equations, revealed one observation at a time, whispering the language of reality. To observe M87 is to read the cosmos in high contrast. It outlines the edges of everything we know, and sometimes, just sometimes, those outlines look like the frame of something more. In the next chapter, we turn back to Earth, back from the edges of theory to what black holes like M87 pace mean to us, not philosophically, but practically, how they shape understanding, how they influence technology, and how a blurry ring of orange and shadow may be one of the most important images ever taken. You've seen it, simplistic at first glance, a blurry circle of light, like a coffee stain left on paper. But that image of M87 Demis is more than a photograph. It's a signal, a signpost, a shift. It represents the moment humanity didn't just theorize about the unseeable, we saw it, a black hole, captured not by imagination, but by instruments, data, coordination, and pure curiosity. And now it asks us another question. What does this mean for us, back here on Earth? Sure, M87 Nene is 55 million light years away. It's not going to swallow our planet. Its gravitational pull exerts exactly zero influence on your morning coffee, your city skyline, or the orbit of the moon. It's a silent god watching from the outskirts of the Virgo cluster. And yet, Its implications ripple across everything we know and everything we will come to know. Because black holes like M87 Weeks aren't just scientific curiosities, they underpin modern physics, technological innovation, and philosophical shifts that are already redefining the world we live in. Let's begin with the most immediate connection: Einstein's theory of general relativity, which M87 Coe helped confirm in spectacular fashion. This century old theory describes gravity not as a force, but as the warping of spacetime, and black holes are its most extreme predictions. For decades, general relativity had been tested in planetary orbits, light bending around stars, and time dilation between satellites, but nothing could confirm its accuracy under extreme gravity until the Event Horizon Telescope revealed the near perfectly predicted shadow of M87. That tells us something crucial. The equations we use to understand gravity work. They are not just ideas, they are tools. Validating them against the deepest wells in space gives us confidence in using them to engineer technology, plot interplanetary missions, and even shape futuristic concepts like gravitational propulsion or warp theory. And that leads us to something very real. Our daily lives already depend on understanding gravity correctly. Take GPS, the very satellites that guide your phone through a city, name hiking trails, or track global logistics, use adjustments baked in from Einstein's equations. Without correcting for gravitational time dilation, the way clocks run differently depending on altitude, the GPS system would accumulate errors of about 10 kilometers per day. That's the power of physics. That's black hole level math woven into mundane life. M87, in many ways, grants that math stellar authority. It's like seeing a bridge built 100 years ago, and, for the first time ever, watching it hold under 1 billion tons of weight. Suddenly, you know you can build higher, push further, reach farther, but the impact runs deeper. The study of black holes, especially supermassive ones like M87 counts, is unlocking a larger story: how the universe evolved. We've learned that black holes are not isolated monsters sitting at the centers of galaxies. They are key players in those galaxies' creation. M87, for example, didn't just form in a galaxy, it helped shape its galaxy. Its jets, those massive beams of high energy particles shooting into intergalactic space, are powerful sculpting tools. Scientists now know that those jets heat up and push away gas clouds in their host galaxies. That heat regulates star formation, controlling when and where stars can be born. In smaller galaxies, this kind of activity can completely quench star birth, creating red and dead galaxies filled with old stars, but no new ones forming. In larger ones like M87, it creates balance, fueling growth when possible, choking it back when necessary. So understanding M87 techs is to understand galactic evolution itself. In its silent pull and explosive outward push, it dictates the rhythm of an entire galaxy's heartbeat. And that means learning about black holes doesn't just illuminate the far reaches of space, it brings us closer to understanding our own cosmic address. How did the Milky Way grow? What role did its own, smaller, supermassive black hole, Sagittarius A, play? Could galaxies have not formed at all without these gravitational anchors? As more evidence gathers, it suggests that black holes may be essential to how the structure of the universe works at every level, from interstellar gas clouds to galaxy clusters. But all of this is, in a way, technical. There's another layer to M87 Pang's impact, perhaps the deepest one of all, what it does to the human mind. Because seeing the image of M87, that great ring, deforming space time itself, forces us to confront something humbling and grand, the fact that our species can reach beyond Earth, that we can take tools, ideas, thousands of years of mathematics and thought, and point them at a dark patch of sky and bend light into picture. It tells us that knowledge is not limited to scale. You can be a fragile, two-legged organism clinging to a speck of dust and still make sense of giants, still chart the oceans of space-time, still weigh the masses of dead stars from the safety of your living room. ME7, in its stillness, reminds us what's possible. It shows us that we can work together across nations, across disciplines, across wavelengths. The image wasn't taken by a lone scientist. It was created by a team of hundreds across 6 continents, processing data with precision, trust, and vision. It shows that cooperation leads to clarity in both science and in society. And still, in all its grandeur and inspiration, M87 Toys is just one black hole, just one galaxy, just one shadow carved from light 55 million years ago. What happens when we capture more? When telescopes improve? When we stitch together informal images into motion, real-time frames of matter swirling into darkness? These aren't pipe dreams. They're part of projects already underway. Black hole movies, 3D maps of the event horizon, studies of how gas crosses the edge. Perhaps, one day, even modeling what happens inside, safe in the knowledge that the math is sound, stable, sustainable, and the spin-off technologies, they're already growing. Better imaging techniques, smarter data processing algorithms, satellite synchronization systems, high-frequency physics used in medical technology, fundamental research feeding invention in unpredictable ways. Just like how studying relativity made GPS possible. Understanding M87 might one day help us reach Mars, or map exoplanets, or even manipulate gravity itself. Because once you've been to the edge of understanding, once you've stared into the abyss and caught a picture, you don't turn away. You grow, you expand, you build better bridges. In the final chapter, we return to where we began, not just to the black hole itself, but to everything it has come to represent. M87 is no longer just a point in the Virgo constellation. It's a symbol of science, of mystery, of the ever-growing human horizon. A single ring of light encircling a darkness that defies comprehension. That's the image the world saw on April 10th, 2019. The silhouette of M87 tags, cradled in golden plasma, floating 55 million light years from Earth, and yet somehow closer than ever. In that image, grainy and glowing, was more than just a cosmic object. It was a message. We've come this far, across millennia, through myths and equations, star charts and quantum mechanics. Humans have stared at the sky and asked what lies beyond. For centuries, black holes were just theories, consequences of mathematics, too heavy to ignore, too strange to believe. But now we have seen one, and not just any black hole, a colossus, a cosmic heavyweight, reigning in the heart of a galaxy larger than our own. This is M87, and what it represents for science, for civilization, and for the future is profound. Its shadow is a cosmic milestone, like the first footprint on the moon, or the crackle of a voice calling, Houston, the eagle has landed. It's one of those rare moments in history when something formerly invisible, intangible, theoretical becomes undeniably real, and yet M87T's importance stretches far beyond the power of its image. It embodies growth, scientific, technological, philosophical growth. To create the Event Horizon Telescope, scientists had to link observatories around the globe in perfect coordination, not metaphorically linked, physically and precisely united in data collection, atomic clock timing, and sky targeting. It was the first Earth-sized lens ever constructed, proof that borders can vanish when curiosity comes first. It also embodies mystery. Beneath all our calculations and models, M87 guards secrets we still cannot reach. What lies at its center? What happens to time inside it? Is it a gateway, a final page, or something neither beginning nor end, but truth, yet unrealized? No amount of high-resolution data can erase the feeling that black holes may hide answers not just about stars and galaxies, but about reality itself, and it embodies perspective. M87 dwarfs our solar system. Its gravity tames stars, sculpts galaxies, and ejects matter at near the speed of light. And yet, it did not care when we took its photo. It spins with the same silent grace it always did. What changed wasn't the black hole, it was us. We changed. We proved that a species born beneath clouds and bound to one planet could reach across time and darkness, capture an image of the void itself, and begin to understand it. And this is the legacy of M86 here. It humbles us, grounds us, and inspires us all at once. It shows that there are still dragons on the map of the universe, still edges to explore, still shadows to chase. It reminds us that science isn't about having all the answers. It's about knowing that some questions are worth asking. Even after thousands of years of trying, it invites us to dream, not wildly, but responsibly, that perhaps, a century from now, another image will flash across a screen, crisper, clearer, richer in color, and show us another black hole in motion. Not just one ring, but many. Not just questions, but patterns. Not just symbols, but understanding. M87 also reminds us that we're part of something much bigger, that our lives, fleeting, fragile, flickering like sparks, still matter because intelligence matters, curiosity matters. The universe has been around for billions of years, and yet only recently, just recently, part of it began observing itself. That's what we are, the universe, looking back, through telescopes, through code, through wonder, and what it sees through the lens of M87 takes is breathtaking. Not just a monster lurking at the galactic center, but a kind of self-portrait drawn in gravity and light, a symbol of what we can achieve, a reminder of what we still don't know, a quiet beacon from the edge of forever, gently illuminating what's possible when we align our tools, our ideas, and our will. So the next time you look up and see Virgo's stars glimmering above the earth, try to remember you're looking in the direction of a shadow, one that took millions of years of travel, one that bent light into a ring of knowledge, a ring that marks an era, an age where darkness no longer means ignorance, where a blurry photo can become the sharpest vision we've ever had. May 7 will continue to spin, to pull, to radiate, to reshape its galaxy for billions of years to come, and we will continue to learn from it, to fall into its mystery, not with ships or shuttles, but with questions, with mathematics, with art, with stories like this one. The shadow of M87 is not the end, it is the beginning of seeing the universe, not just with eyes, but with understanding